For our Chapter 2 review, we talked about the Cambrian Explosion and tropical Alberta. So the Cambrian Explosion, first we had to learn about fossilization. And fossilization is a process like death, burial, preservation, discovery, recovery. In this process, we have things that get preserved under layers and layers of rock. It produces a mold. Eventually, the bone and other tissue is replaced by minerals that seep into it. This causes them to be preserved quite well, so we see this mold form in the sedimentary rock layer. The mold gets filled with other sediment and particles and eventually hardens over time. Some examples. Okay, when things become petrified, again, this is when organic material, like the wood in a tree bark, gets replaced with inorganic material like minerals, and it hardens, so it's much easier to preserve. Soft tissues are more difficult to preserve, but they can be fossilized, again, if that organic material is replaced with minerals and other things that will harden and last over time. The Burgess Shale is really important because it shows a lot of evidence for the Cambrian Explosion. So the Cambrian Explosion is when we had a huge evolution of a whole bunch of new animal species and body types. And the Burgess Shale had very, very well-preserved fossils of many of these new organisms that evolved. The Burgess Shale was pretty unique because we see all of these types of organisms. And the nice thing about it was, due to these underwater avalanches and mudslides, okay, these organisms got trapped and there was no oxygen underneath this mud to decompose them. So they were preserved really, really well. These are all aquatic type species because at that time, 500 million years ago, where Alberta is now was once underwater, and it was much closer to the equator. So in the Burgess Shale, we had animals that were underwater, mudslides trapped them, low oxygen allowed them to be well preserved. Eventually, over time, from plate tectonic movement, which we'll get to in a second, this, once underwater, got pushed up into a mountain range. Erosion over time eventually exposed what was once the floor of this seabed, and the exposed rock contained all of these fossils. So the Cambrian Explosion was a period of time where we see most of the basic body types that we see now. So modern organisms, a lot of those kind of basic designs appeared in the fossil record during the Cambrian Explosion. There's a 20 million year span where most of these body types evolved, which in the actual geological time scale is quite a small period of time. So nearly all modern groups can be traced back to some common ancestor from this period. The other thing about the Cambrian period was that because of this huge explosion of all these species, we had a very large abundance of organisms. Over time, these underwater organisms eventually die and start decaying. So plankton, also one of these. Again, this was all aquatic back then. When this stuff started to decay and decompose, a lot of the oxygen got removed from the bacteria that were doing this decomposing. And after a very long period of time, about 380 million years, layers upon layers of sediment started piling up on this dead, decaying organic matter. So all these dead organisms and plants and plankton. So this created a lot of heat and pressure from all of that sediment over time. Eventually, it compressed it so much, so we take out all the oxygen. What do we have left? Carbon and hydrogen, the two ingredients that we need to make petroleum. Okay, these are examples of drilling rigs. All of this dead, decaying matter was trapped between rock on the top and bottom, which created what we call a petroleum trap. So it's a very large reservoir of this petroleum stuck between these rock layers. Again, lots of heat and pressure over time. This is why we call gasoline and things like that fossil fuels, because it's made from very, very old dead organic matter that decayed and converted into this petroleum. Geologists start looking for it. They look on the Earth's surface. Well, the problem is we can't see it. Outcrops is when we have something that was once underground now being exposed, like the Burgess Shale would be an outcrop. All this petroleum, though, is still trapped way beneath the Earth's surface. So we use these things called drill cores to kind of sample what's below the Earth's surface. Here's an example of a drill core. So you can see by looking at this, we've got different layers in this rock, and some of these might be petroleum. So they put this cylinder in the ground, pull it out, and then examine all those different layers to see if there's petroleum. Another very effective way is to use seismic waves. Okay, they can do this by creating large explosions to send these vibrating sound waves through the Earth. The waves will always change their speed and direction every time they encounter a new layer. So this is how geologists can tell when those rock layers are changing beneath the surface, every time they see a change in the wave pattern. They use a seismograph, which is the machine that actually records this, and it produces a seismogram, which looks like this. A geologist can analyze these changing wave patterns to look at the different rock layers and see perhaps if there is petroleum trapped under the Earth's surface. Earthquakes are a natural source of these waves. Okay, it's vibration in the Earth, and it's caused mainly by the motion of tectonic plates. These four terms are important to know when it comes to earthquakes. A fault is a crack in the crust. This is where two tectonic plates are colliding together. A focus is where we first see a breaking point. Epicenter is directly above this focus. Okay, and then subduction is when we see the movement of one tectonic plate over another. Okay, a couple types of seismic waves. One of these were P waves, meaning primary. They travel fast, so they arrive first, and they travel longitudinal, which means that they vibrate particles parallel to the way they're moving. They move like this, a series of expansions and compressions. The S waves are secondary because they move a little slower and they only travel in solid. They do more damage than P waves, though, because they produce these large amplitudes. So that means the height of the wave is quite large. They travel like this instead of a series of compressions. They are transverse because the particles vibrate perpendicular, so meaning the opposite direction of the way that they're traveling. Okay, speed increases as you move through the Earth because material gets more dense, and we use the Richter scale to measure these earthquakes. So like a 3 would be barely detectable, a 9 would be more like the Japanese earthquake. Okay, another type of wave that we see is a sea wave, a tsunami, that's set off by an earthquake. So what happens when you have these underwater plates that suddenly snap due to a buildup of pressure, okay, it displaces a huge amount of water. That water's got to go somewhere, so it gets pushed up, which generates very large waves that actually tend to be the most damaging part about an earthquake. The earthquake itself usually doesn't cause as much damage as the aftermath of these tsunami waves.